In this video, we're going to talk about handling ARP failure between two routers or two layer 3 forwarding devices, and being resilient against ARP failure within the routing protocol that you're using. This is something I ran into recently, and I realized that we often talk about handling failure of a lot of different things, and handling failure of the link, of the optic, of a line card, of the route processor, of the routing protocol process itself. But very rarely, I don't think I've ever seen anybody talking about handling failure of ARP. And ARP is a control plane process. So to me, it's susceptible to failing. It's possible that ARP doesn't work. And I started realizing that there's a lot of different scenarios you could come up with where that would break ARP. ARP can be policed with control plane policing. That can be something that drops ARP packets, ARP frames. You can have some device in the middle that's rate limiting broadcast traffic that's doing dynamic ARP inspection and it's misconfigured or something, so it's dropping ARP. Maybe the memory that a router has allocated to the ARP process has become full, so it can't resolve additional ARP entries and place them in memory. There's just different situations where you could come up with where ARP would stop working. And the dangerous thing is that if ARP stops working, the routing protocol may stay up. So in that situation, you've ended up blackholing traffic. And so it's a very dangerous failure scenario. And I think it's important to consider this and to consider handling failure of ARP, being resilient against the failure of ARP. So to explain this scenario, to explain this issue, I've got this scenario here with Anycast DNS set up. And before we get into this, I just want to mention that this can really just be any kind of active-active scenario. The overall theme here is that you've got some route where it's best via one path and there's a backup path via some other path. So like here in DC1, the best path to 10.255.251 is here via the DNS server locally. There's a backup path via R2 to DC2, and this cloud here is just representing any kind of connectivity between R1 and R2. It could be MPLS, it could be layer 3, just basically IP reachability, whatever it is. But the main point here is that R1's best path is via locally DNS1, R2's best path is locally via DNS2, and they each have a worse path that's held as a backup path. So if any one of these if the route locally fails, we're just going to fail over to the other path. So, imagine that top of rack switch fails here. There's hosts in DC1 that have configured the DNS server as 10.255.255.1. So it's really no problem for this switch to fail, right? Because whatever routing protocol is running between R1 and the top of rack switch is going to detect this failure. Even if it's a static route, the link is going to go down. That static route is going to get withdrawn from the RIB. And what's going to be left is this route via R2 to the DNS server in DC2. And the host will just start using that DNS server. But what happens if ARP fails and we're using, for example, OSPF here between the switch and the router? Well, we're imagining that OSPF is already established and some problem with ARP has happened. The ARP process has just crashed for whatever reason. Of course, it's very unlikely, but just imagine that it's a possibility. It could happen, and ARP could stop working. So R1 sends an ARP request to top of rack switch 1 for 10.0.1.2. The switch just doesn't reply. Now R1 has an incomplete ARP entry for 10.0.1.2. But OSPF stays up because OSPF hellos are multicasted. So maybe the top of rack switch's OSPF process is still functioning fine. It's sending and receiving multicast traffic for OSPF hellos. OSPF adjacency stays up. The route for 10.255.255.1 via 10.0.1.2, known via OSPF, is continuing to be installed in the RIB for R1, but R1 cannot put a Ethernet header on traffic destined to the DNS server because it doesn't have a complete ARP entry for the next hop. So this is really a very bad failure scenario, and to resolve it, you would need somebody to go in and bring down OSPF or something. It requires manual intervention. And, in networking, we always want to avoid something like that. We want our routing protocol to handle any failure that could break reachability. And we want it to just automatically take this route away and go to DC2, because that's why we have this active redundancy, right? So we're going to get into this even more in depth. But I thought at first, now that we've kind of explained the problem, it might be useful to just review ARP. Of course, ARP is a very simple protocol, but when I come across these kind of scenarios and go into them in depth, I like to just review the technology that I'm using, just to feel like I've got a really good grasp and a fresh understanding of the protocol that we're talking about. So I've got a packet capture here of ARP, and ARP is a very simple protocol, and of course it stands for Address Resolution Protocol. And what's interesting is that I believe it was created to handle any type of layer 2 or layer 3 protocol. So it can be used just to, in general, resolve a layer 3, the layer 2 address for a given layer 3 address. So if we back up and we say, well, why do we need to do this? Well, it's because on R1 here, it's going to have some routing information for, a route via 10.25251 via some layer 3 next hop, 10.0.1.2. It can know this in many ways, OSPF, ISIS, it can be a static route. But the point is that somehow the RIB has this route, and the RIB is operating at layer 3. It has a route via some layer 3 next hop. But these routing protocols don't exchange the associated layer 2 address for these next hops. That's the job of ARP. ARP needs to resolve the MAC address to use for the next hop. So ARP lets us resolve the layer 2 address, the lower layer, of any layer 3 address. So of course nowadays we're only going to see that the hardware type is ARP. Ethernet. So this is the layer 2, hardware is layer 2, protocols is layer 3 here. So these fields, it's a very simple message. It's what is the layer 2 type, Ethernet, what is the layer 3 type, IP. Of course, back in the day when this was invented, it was very useful to know, because you could have DECnet, IPX, AppleTalk, etc., etc. These days, of course, it's pretty much always going to be Ethernet is layer 2, IP is layer 3, IPv4 specifically, because of course for IPv6 we're using neighbor discovery to do this process. Okay, then we've got the size of each layer 2 and layer 3 address, because this could be something besides Ethernet. It handles that. But so we've got 6 bytes for the Ethernet address, 4 bytes for the IPv4 address. And then the opcode is either just 1 or 2, request or reply. So very, very simple. Then we've got sender layer 2 and layer 3 address, target layer 2 and layer 3 address. So here the sender fills in, this is my layer 2 address, this is my layer 3 address. The target layer 2 address is what we're trying to resolve. Generally, you'll see this as all zeros. Here in this packet capture, it's all Fs. It doesn't actually matter what this is, because for an ARP request, this is not, this is like dummy filled information. It's known that this is what we're trying to resolve. Then the target IP address, the target layer 3 address. And of course, this has to be broadcasted, right? Because we don't know the destination's layer 2 address. That's exactly what we're trying to resolve. So this has to be broadcasted to all hosts in the LAN. Now, the reply, the only difference here is just, the opcode is to reply. And then the host that's replying to this fills in its own MAC and IP. So here's the resolved MAC and the sender MAC this time. And then it fills in the target MAC and IP that it knows from the request it just got. And then it unicasts this reply. So this saves on some broadcast traffic, right? Because we know which host is requesting this information, so we just unicast it back. And you can see that the destination MAC address matches the target MAC address of the ARP reply. So I hope you can agree that this working of ARP is quite basic and really not complicated at all. Maybe there's a little bit of complication with caching ARP because, of course, we can't do this process for every single packet that we want to send, right? I mean, imagine if a host didn't cache this information, it would send a layer 3 a packet to the next hop. It'll say, okay, wait, I need to know the Ethernet address. Let me ARP. Okay, I've got it. Put it on the packet. Now another packet comes. I need to know the layer 3 address and continue this one ARP per packet that needs to be sent. Of course, that makes no sense at all. So we have to cache this entry, this ARP resolution. And the time that you cache this for varies a lot by implementation. So hosts might cache this for as low as a minute. Routers could cache this for as long as 4 hours. On Cisco, the default cache timeout is 4 hours. I believe on Juniper, it's like 20 minutes. Generally, on all of these platforms, you can adjust the timer if you want to, but you want some balance between not sending too much ARP traffic because the ARP resolution is most likely not going to change very often, but yet being able to handle if that value does change. You want that resolution to that entry to time out at some point, so you can handle if the IP does move to a different MAC address, to like a different host or something. And of course, talking about this naturally the conversation goes to gratuitous ARP, right? So if this is what VRRP and HSRP use to announce that the IP is now known via different MAC. With gratuitous ARP, typically it's an ARP reply that has the same sender MAC and target MAC and sender IP and target IP. So it's the same. It's the host resolving itself, I guess, but it's just announcing that, hey, this is the resolution for this IP address. So that all hosts on the LAN update their ARP cache for that IP address. So there's some other optimizations that can happen with ARP to reduce the broadcast traffic on the LAN. For example, if a router is the router on the LAN and there's two hosts sending ARPs to each other, the router can notice the ARP request because, of course, the ARP request is broadcast and the sender is filling out its layer 2 and layer 3 address. So the router can see this and say, okay, host A is trying to resolve host B's address, but I can notice that host A has put its layer 2 and layer 3 address in this ARP request, and I can use that to refresh host A's ARP entry. Now, of course, the reply is going to be unicasted back, so the router or some other device on this LAN is not going to be seeing that and can't use that for some optimization. And then just ARP refreshes in themselves can be unicasted. So let's say we've got a Cisco router, it's got an ARP entry. The time value is now at 3 hours and 59 minutes. So it's about to expire in 60 seconds. The router can unicast a ARP request. So instead of this being broadcast, the ARP entry is valid right now. So it can send it directly unicast to the MAC address that it has for the ARP resolution. And hopefully that device that host will reply, and then that refreshes the ARP entry. If the host doesn't reply, then the ARP entry times out. The next packet that the router receives destined to that IP that it has to resolve is going to go through the whole ARP resolution process again and send a broadcast frame. Okay, so I think that does it for refreshing ARP. So back to this this scenario, let's go through each IGP individually and discuss how does ARP breaking affect neighborship formation, bringing up the adjacency, and how does ARP breaking affect if the adjacency is already established, what happens with routing? Does the adjacency stay up or not? Okay, so first we'll talk about OSPF. So I've got an OSPF packet capture here. And we can see that, of course, the hellos are multicasted, and the database exchange process is unicasted here. So if ARP was broken from the beginning, neighbors will be stuck in xstart or exchange. And This may vary depending on what network type you're using. I didn't dig into this too much because it's not super important for this discussion, because the ultimate issue is that once the adjacency is established, ARP breaking will not bring down the neighborship, the adjacency, because hellos are multicasted. So to summarize for OSPF, ARP is broken at the beginning, neighbors may not come up. ARP is broken in the middle, the neighborship will stay up. For ISIS, it's even less resilient against ARP failing, because of course ISIS operates at layer 2. You can see here the LSP exchange, the hellos. None of this has anything to do with IP. So ISIS doesn't care if you can resolve ARP. It doesn't care if there's IP reachability at all. It's just operating at layer 2 and exchanging IP reachability information. But ARP being broken from the beginning has no effect on ISIS. IS neighbors will form, routes will be installed in the routing table. If ARP is broken in the middle, of course, ISIS hellos continue to work. So you get the same problem if ARP is broken. For EIGRP, what's interesting is that the updates at the very beginning of bringing up the neighbor are unicasted. So if ARP is broken, the updates won't work. You'll be able to form neighbors and the neighbor will come up, but there'll be no routes installed from that neighbor. So EIGRP does have some resiliency against ARP being broken, at least from the standpoint of ARP being broken at the very beginning. But if ARP breaks in the middle, once the neighbors are already up and the updates have already been sent, of course, all these routing protocols aren't sending periodic updates like as in RIP of the old days. It's incremental as needed. So you could have the same problem with OSPF and ISIS, that if ARP breaks in the middle, EIGRP neighborship continues to stay up because, of course, the hellos are multicasted. And you have the same problem of black holing traffic. Now, I guess the only other IGP you could call it would be static routes. And of course, static routes are there's no discovery at all. The static route is going to stay up even if ARP is broken, because all you're doing is just statically saying, for this route, this is my IP next hop, and then it's the job of the router to resolve ARP when there's a packet to deliver using that route. But the static route will stay up even if ARP breaks at some point. Okay, so now, what is the solution to this? How can we achieve failover, and how can we be resilient against ARP failing? Well, the overarching concept here is that we need to detect failure of the layer 3 data plane, of IP traffic not working in the data plane. So anything that involves unicast traffic between the two routers, between the neighbors and the routing protocol, that's going to detect and be resilient against ARP failure. And when I'm saying resilient against ARP failure, what I mean is that it's going to bring routing down. Not that it continues to work even if ARP fails, but just that in the situation where we have active routes, if ARP breaks, we want that route to be withdrawn. We want it to fail and not stay up. So one method could be using IPSLA, so like a static route with IPSLA. And these solutions are kind of in order from least recommended to most recommended. So IPSLA, it's not a great solution, but it is a solution. You would have some IPSLA operation that just pings the next hop. So here you have an IPSLation on router 1 that pings 10.0.1.2, and then the static route for this address 10.255.251 via 10.0.1.2 is tied to the IPSLA operation. If the pings go down, the static route is withdrawn, and then R1 will only have the route via DC2 left in this routing table. You've achieved failover. Another option would be just using BGP, because BGP, of course, runs on top of TCP. So BGP doesn't hide ARP failure because all the messages are unicasted between the neighbors. With the IGPs, we have multicast because we dynamically discover neighbors on the link, right? But with BGP, we don't do that. We need to manually specify the neighbor's IP, And then the router brings up a TCP session, this unicast, to that IP. So the open message is unicast, keepalizer unicast. So if ARP fails at the very beginning, BGP just won't come up. If ARP fails at some point in the middle, the keep alives will time out. So you will rely on the hold time to expire, which by default is like 3 minutes. So you could set this to some lower value. Or, just it's useful to failover in 3 minutes than never with the other IGPs. So BGP is resilient against this problem. And finally, the very best solution would be just to use BFD. And BFD can be used with all of these protocols we've been discussing, including static routes. So it's obvious that BFD is resilient against the control messages breaking, right? So just as a very quick recap, this is not meant to be in depth about BFD, but BFD uses either control packets, BFD control messages by themselves, or it can use control with echoes, and the echoes are looped in the data plane. So it's obvious that the control messages detect ARP failure, right? Because this is unicast between the two devices, just the same as BGP. So here in this packet capture, we can see that there's like R1 and R2, right? 10.1.2.1 and 10.1.2.2. And their MAC addresses match the last octet where this ends in 1 and this ends in 2. So the BFD control messages are just regular unicast traffic. So if ARP is broken, the BFD control messages will stop working. Well, what about echoes? It might be a little less obvious if the echoes are resilient against ARP failing, because the echoes have an optimization where the destination IP is the same IP as the source IP. So here R1 is sending a BFD echo where the source IP is itself, the destination IP is also itself, but the layer 2 header is the same as usual, where the source MAC is R1, the destination MAC is R2. So because of this, the echoes are resilient against ARP failing, meaning that if ARP fails, the echoes will fail to be looped back. Because, first of all, R1 would need an ARP resolution for R2 to know what to put in the destination MAC header. Secondly, R2 needs to have a resolution for this destination IP address, which is R1's IP address, to be able to rewrite the layer 2 header. So isn't this a control plane process? How is this looping it in the data plane? Well, generally in the hardware, you install the adjacency information and with the fib. So R2 would receive this packet that's destined to its own MAC address with destination 10.1.2.1, and in hardware, it rewrites the layer 2 address. It has the rewrite information on hardware to rewrite that to destination of the MAC ending with 1, and this will loop it back to R1. So the echoes actually provide validation that ARP is working in both directions. Just one echo provides this validation. So really the best solution to being protected against ARP failing is to just use BFD, because this works for whatever routing protocol that you want to use. It's kind of interesting to note that we sometimes just think of BFD as being useful in situations where there's some like layer 1 device in the middle. Like you've got some switch or some NID in the middle. And of course, the argument for BFD is that, well, if this link goes down, this link is still going to stay up. And the switch is going to rely on the routing protocol hold timer to expire to reconverge. It's not going to quickly detect link failure. So BFD solves this problem. But looking at BFD and consideration for handling ARP failure, it gives us a different appreciation for what BFD is actually doing, which is that at a high level, more holistically, what BFD is doing is fully validating the layer 3 data plane. It's validating that R1 can send a packet with its own destination IP address, and that the other router is going to correctly loop that back to itself, and R1 can then receive it. It's fully validating the end-to-end layer 3 path, and that traffic is working in the data plane. And as a side effect, BFD does handle the failure situations where there's any layer 1 or layer 2 switch in the middle of this path, because BFD's job is to validate the basically IP next hop reachability to the next hop um, that's learned via the routing protocol. So with this in mind, it makes you think, well, maybe we should just use BFD everywhere, because if that's really our ultimate goal for detecting failure, is that the IGPs like OSPF, for example, the hello is just validating that multicast traffic can be sent between the two routers, and that their OSPF process can receive the hello and send a hello. OSPF is not fully validating that the next hop is reachable. It's not doing. That's why you need some kind of IPSLA operation or something, with like in the case of the static route that tied to it, to do that extra validation. So, but we want to handle more failure scenarios than that. For example, in this video, we want to handle the failure scenario of ARP breaking and something breaking IP reachability between the next hops. And that's the protection that BFD gives us. So this really makes a strong argument for you might as well just use BFD everywhere to give you the most protection possible. So yeah, I hope this has been interesting, kind of made you think about failures in a kind of a different way, an out of the box way, because talking about handling the failure of ARP is just something I've never really seen discussed too much, but it's a possibility. So let me know if this is something that you've come across, if you've thought about and handled in a different way, and yeah, I hope this has been interesting.